will start at 3:05 at the same time. The keynote talk session is in the meeting room and the invited talk session is in the other meeting room. Finally, please come back to this meeting room at 5:20 as we will have the closing ceremony, in which we will announce the best oral presentation awards and the most impact awards for our invited talks. We will also announce the organizers of the second iFOSA International Forum next year. Yeah, just a brief introduction. Okay, it's 2 o'clock. I think we can start. Good afternoon, good morning, and good evening, everyone. It depends where you are. Welcome you to our plenary talk. I'm Feng Shijie from Nanjing University of Science and Technology. It is my great honor to be the chair of this session. In this plenary talk, we invite Professor Gunther Notny. He is a full professor at Technical University Illinois, and he is the chair of the Group for Quality Assurance and Industrial Image Processing. His work focuses on the development of 3D and spectral image acquisition methods, high-resolution surface and shape measuring methods, application of wavelet methods in optical metrology, optical techniques of system development, and the development of terahertz systems. Today, he will talk about the real-time multimodal 3D imaging. Now, let's welcome Professor Gunther Notny.
Okay. Hello, everybody. I'm Gunther Notny from Germany. Thank you very much, Xi and Song, for inviting me and giving me the possibility talk to real-time multimodal 3D imaging. As she mentioned it, I'm with the Technical University in Ilmenau and also with the Fraunhofer Institute of Applied Optics and Precision Engineering. In the last years, we have dealt with different methods of 3D imaging, and the latest developments have been in the field of multimodal 3D imaging. What we mean with, or what is the content of my talk at first? At first, I will give a brief description of the multimodal 3D imaging, what is meant with that, and then I'll shortly describe our method for real 3D imaging techniques using pattern projection techniques. And after that, I combine these methods and deal with multimodal 3D imaging, especially with the topic of calibration of multimodal 3D imaging techniques. And last but not least, I will show you on 3 different applications how this multimodal 3D imaging technique can be very well used. Multimodal imaging is in principle very well known, especially in the field of medicine. There are a number of different techniques. Multimodal imaging, or often also called multiplexed imaging, refers to a simultaneous production of signals from more than one imaging technique. In medicine, there are different imaging techniques like white light or digital X-ray or near-infrared fluorescence imaging. And to combine these image modalities, one can find and separate, for example, tumors and find them on the right position. Or also here on the right-hand side, the combination of PET and CT measurement for detection of metastasis. In our field, we don't deal with a combination of 2D imaging technique. We will combine what happens. We will multimodal imaging in our case means a combination of 3D images which are captured by a 3D sensor, resulting in 3D data of the object or of the scene, and in combination with color imaging, that is very well known, but also with a combination of spectral information using multispectral cameras or also temperature data, so that we can describe the object scenes with different image modalities. And multimodal imaging refers to the combination of image modalities for any spectral range and dimensionality. And so at the end, we will have an extended object or scene description. That is shown, will be shown here on the right-hand side, when you have here the object, and in our case, the object at first by a 3D sensor, a 3D data are captured, here in this case using a stereo arrangement, and then different image modalities are combined with them. For example, the color of the scene is captured, the multispectral data are captured. Multispectral data means measurement at different spectral ranges. Infrared data are captured, shortwave infrared data can be captured, or polarization data can be captured. All these image modalities are combined to the so-called multimodal image data. Now, at first, I will come to a short description of the 3D imaging technique which we use. There are a couple of different 3D imaging techniques available, which cover a great range from measurement from different object size, realizing different depth uncertainty, which is shown here in this graph, recently published by Marugo et al. And there are a couple of different techniques. They are mostly for 3D scenes, passive stereo, active stereo. That means the projection of a pattern onto the object and the observation by 2 cameras, time of flight, and triangulation methods are in use. But of course, they have different real-time capabilities. One can capture different object size, which is shown here. The triangulation is for smaller objects, time of flight. Based systems often used for objects in the range of 1 up to 10 or more meters. And they have different uncertainties which can be reached, and in dependency of the application in mind, one have to do the right change, and especially one have to take into account the real-time capability. That means at which speed the 3D data can be captured. At least we are interested to have an real-time data, that means more than 50 or 60 3D data per second. For For this, often used 3D imaging techniques are very well known, like these single shot techniques, which are shown here. That is the very well known Microsoft Kinect system, where a structured light system with a single shot, the 3D data are captured using the analysis of these point dots or the inter-real sensor. And on the other hand, there are the time-of-flight cameras. Recently, the newest one is the inter-real sense L515, the LiDAR camera. With these systems, one can reach real-time capability 30 up to 60 Hertz. One can measure a 3D object some meter and square, but the uncertainty is not so high. It's in the range of 10 up to 10 millimeters, which might be possible too low in a number of applications. I will show it later on. A very well-known technique for 3D capturing is also the phase-shifting fringe projection technique, where the object under measure is observed by two cameras, are shown here. The object is in the middle. Then projection system project fringes, phase-shifted fringes normally onto the object, and using the phase formula, which is shown here for phase step technique, and in combination with a gray code pattern, one can capture the 3D shape of the object and analyze the 3D data by a triangulation between the two cameras. This is a very well-known technique, very often used, and here hopefully you have seen it on the right by capturing the data of this mouse here by a projection speed of up to 60 Hertz. In this case, one can reach very good 3D data with uncertainty below 0.1 millimeter. You see here the point cloud, very smooth, no errors, very fine technique. But most of the objects which we are interested in are not stable. They are moving. And when you use this technique on moving object, then it will become to a number of errors. You see here the point cloud of the object. There are some so-called phase shifting errors, phase errors, by this periodic structured onto the object. Some points are missing, and it is clear this kind of projection technique is quite difficult to use for moving objects. To overcome this problem, we have introduced the so-called projection technique using the projection of aperiodical sinusoidal fringes and use the method of so-called temporal correlation of patterns. What is meant with this technique? You have also the object under measure, two cameras here shown on the left and on the right hand side, the projector in between, but you project not sinusoidal fringes, you project aperiodical sinusoidal fringes. That means you see here on the right, on the top right, across to this pattern. You see here that at each position in the red, green, or yellow or blue curves, that the phase, that the intensity is shifted. The phase is shifted, the modulation is shifted, so that you have arbitrary so-called aperiodical sinusoidal fringes. Of course, you can't use the well-known phase shifting technique to find the right point onto the object. Here, between the two cameras, we use the so-called cross correlation or the correlation techniques. That means one look at every point of the object to the stack of intensity values which are captured for the different projection intensity, and look at which point the same stack of intensities takes place. And that is done by the correlation technique. The formula is shown here. we do a correlation of a sequence of fringes. It is a stack of the intensity values between the cameras. That has a great advantage, this correlation, because you have to find only the right or the same stack of intensity at the camera on the left and on the camera on the right. But you need no knowledge of the intensity values or that can differ between each frame. This technique has a number of advantages. There is no requirement on the accuracy of the pattern because you have no knowledge on the phase shift. The intensity varies only. You have only to ensure that the intensity changed between each frame, but not more. That means the variability of fringe contrast or modulation has no strong influence. There is no synchronization between the projection unit and camera, only between the camera, and that gives us the possibility for a new kind of projection techniques instead of DMD or LCOS displays. And a projection technique which we have introduced is a so-called gobo projection technique. That gives us the possibility for high-speed or real-time pattern projection. Gobo, what means gobo? Gobo is a stand for goes before optics or graphical optical blackout. That is a simple projection unit here shown on the right or on the top. You have the lamps, you have the gobo, it's like a diaphragma, and this diaphragma is imaged onto the imaging plane here by a focusing lens. And this gobo, in our case, we use a so-called gobo wheel, which rotates and which has some slits on it, and by rotating this gobo wheel, the images are changed between each frame. In this rotation, you can made with a very high speed, and so you are able to project up to 100,000 images per second. In principle, that is possible, and you can realize these aperiodical sinusoidal fringes by the projection of this from the starting point. It's a binary structure. Then you make a slight defocusing of the pattern, and by the rotation you will end with the aperiodical sinusoidal fringes. So you have a very simple, very easy to handle projection technique. We have constructed different kinds of these gobo projection unit and gobo wheels, which are shown here. On the right hand side, the gobo wheel is made of metal. That is for this system here, the stripes onto the object, onto this wheel, are made by laser cutting techniques. And these, of course, can be used for high power lamps or also in the far infrared range. I think my colleague Stefan Heist has been shown it yesterday. And this system has a great advantage that it is heat resistant. On the left hand side, you see a smaller one, a glass wheel, gobo wheel, where the stripes onto the object are made by simple chrome coating. And this type of wheel we often use for when we have an LED as a light source. And on the basis of this, we have realized a real-time 3D sensor, which project here in this shown here in this sketch. We have some near-infrared LED at 850 nanometer, which illuminate this gobo wheel. We have the two cameras on the top and on the bottom. In between the projection, the illumination of the measurements measurement area, and both of the CMOS cameras can capture the images. The device is shown here on the top. You have the two cameras, and in between the projection unit. And with this setup, we have realized a 3D scanning measurement field up to 2 meters in square. We reached depth uncertainties below than 0.1 millimeter, and with a maximum resolution of 4 megapixel, an image stream of 30 3D images per second, with a very low latency between the image of 100 milliseconds. And this 3D sensor now is a basis for our multimodal real-time 3D imaging system. And our laboratory setup, our huge laboratory setup, you see here, we have a 3D sensor. That is the 3D sensor consists on the two cameras here named by number 1 and number 2, these NER cameras, the projection unit in between. And then we have combined it with the different numbers of cameras. Here, number 4 is a color camera, the polarization camera, the shortwave infrared camera, this purple system, and this yellow system, the thermal camera. And so we cover, you see it here on the right-hand side, we can cover a huge spectral range for observing the object or the scene. Also, which are not shown here, we have combined it with a multispectral camera or single cameras at special single spectral ranges. The problem which one have to solve is a pixel-wise assignment or the combination of these 3D data with these 2D data at the different spectral ranges. That means a pixel-wise assignment of the 3D point cloud and the multimodal 2D image data. And for that, a calibration of this complex sensor setup is necessary. That means the determination of the intrinsic and extrinsic parameters of the setup. And so we have to determine the position of the fringe capturing cameras, which are shown here by the green, and the cameras for the different other image modalities shown here on the right-hand side from principle. In the calibration process, we use the very well-known calibration technique using checkerboards or circle boards for the determination. That means the detection of multi-view captured calibration targets, and in order to align the 2D camera of different image modalities to the 3D sensor, the relative pose of these 2D cameras must be calculated, and using this calibration target with a known geometry between the target markers, the 3D sensor is firstly calibrated. This is shown here, and also the 2D parameters or the intrinsic parameters of the 2D cameras are determined. And then we construct the intrinsic and the extrinsic parameters of the 3D, the target markers in the 3D world coordinate system. So we could determine the extrinsic parameters of the 2D cameras using the so-called PNP algorithm, which is shown here. And at the end, we will have the extrinsic parameters of the multimodal camera system. We have a complete description of the sensor setup. That is from the that is also shown here. We have the two cameras of the 3D sensors, NAR camera 1 and NAR camera 2, which detect the markers onto the object. And finally, one have to determine the so-called rotation matrix and translation matrix of the 2D cameras, which are schematically shown here on the left. And the determination of these rotation and translation matrix from these known marker points in the world coordinate system can be done using this PNP algorithm. And at the end, one have the alignment of the 3D point cloud with, for example, the color image, the thermal image, the polarization degree map, or the short wave infrared map. And here you see the formula for that. On the left-hand side, the coordinates, the image coordinates in the 2D images. Here the 3D coordinates, and which in the combination in this formula with this rotation and the translation matrix to combine these data to the 3D point cloud. The calibration process itself takes place as, in principle, as known very well. One has this board. Here, this board has some circular markers on it. We observe it with the different cameras, near infrared or here long wave infrared camera and visible camera. Change the position of the board. Look for the markers on the board, find them, and on the basis of these markers and up to 200 board orientations, one can calculate all the camera parameters using the well-known bundle adjustment calculation, which is known from photogrammetry. But what is the problem with this technique? What one have to take into account? One have especially taken into account that the calibration target must be visible for all cameras. It must be visible in all spectral ranges, in the vis, near infrared, short wave infrared, long wave infrared, and also for the polarization camera. And mostly up to now, as calibration targets, paper printed targets are used, and these are not visible for the far infrared range. Here you see some pictures of this calibration target, and to overcome this problem that the calibration target made of paper or other materials are not visible for infrared cameras, we have developed a calibration target made of plastic. Is an epoxy resin, and the checker part or the material is copper or nickel gold onto the surface, and when we heat these target, this can be seen in the near infrared and also in the visible spectral range, and also due to the heating of the object surface, these metallic parts can very well seen, which is shown here on the right hand side, in the infrared range. And to optimize this the visibility of the target or of the markers, this target we have made an illumination directly onto the target from the left and from the bottom or from beside, with a white light illumination and NIR illumination, and so we can have a very good visibility of these markers in these spectral ranges, and due to the heating also in the far infrared range. And using this technique, we can now calibrate, and using this target, now we can calibrate our equipment for the whole spectral ranges from this visible range up to the far infrared range. And at the end, we came from the 3D data, mixed them up with different image modalities, and have 3D point clouds in real time for different spectral ranges. That means like a multimodal 3D video frame. These data now we use for a number of applications. And the first application which I will show you, is the so-called contactless estimation of vital signs. Vital signs are very well known. The temperature, the fiber, is the respiratory frequency, it's the oxygen saturation, and it's the pulse or the heart rate. And normally, these can be detected, for example, the respiratory frequency and the temperature by thermal images, and the other by a multispectral detector. These parameters that's are, for example, are very critical for corona detection, and the idea which is behind, one will develop a so-called corona gate. A person comes to this gate, and by a contactless determination of all of these parameters, one can find if a person is ill or may be ill or not. But also there are a number of other medical applications, like the contactless sensing in neonatology. These little childs, one should avoid to contact them, and so one is interested to measure all of these vital signs contactless, and not to use finger clips or other which may some disturbance of the skin, for example. How we can determine now, using this multimodal 3D image approach, these vital signs, the heart rate, or pulse, basis on the analysis of the so-called PPG signal, that is the photoplasmography. It's a very strange word. Measurement which is characterized by the measurement of smallest color changes in the near infrared. And we have shown that especially when one measures these small color changes at the wavelengths at 780 and 940 nanometer, one can capture this heart rate very well. The oxygen saturation is characterized by the so-called RR value, or ratio of ratios, which is linear to the oxygen saturation, shown by this formula here. The RR value is this ratio of the 780 nanometer to 940 nanometer. Is a value. These R values are calculated by the alternating and the direct value of the change of the signal at 780 nanometer divided by 940 nanometer. The respiratory frequency one can measure, for example, by the temperature change in the region of the nose or the nostril, caused by inhalation and exhalation, and the body temperature can easily measured, or the best point to measure them is the so-called eyelid corner. All of these parameters you can, as you see, that you can measure it from data from the face, and so in principle we have can use or can build and use for that a multimodal 3D imaging system, which consists of 3D data capturing the face, and the multimodal image data, the color camera, the near infrared camera at 780 nanometer, 940 nanometer, and the infrared camera. And The problem why you will ask why you use 3D images. 3D images are used to find the right position of the measurement regions. This should be done automatically. That means one should find the region of interest, for example, for the measurement of the pulse, this region here in red at the forehead, or the region it's a nostril for the respiratory frequency. And this should be done or will be done automatically by using landmarks and the open face model in the 2D model, but in the 2D images. But when you measure at a moving person, not on a stable or sitting person, you have to take into account that, of course, there is a strong head movement, and to find these region of interest at during the movement and to follow them. For that, you have to use the 3D data. And the 3D data are now used for face tracking and the new localization of the region of interest in space. And so we will end up with a procedure for generation of face tracking model, a new localization of region of interest in 3D space. That means we capture all these multimodal 3D image data. From the first frame, we make the facial analysis in the color images. We determine on the basis of these data the region of interest in the 2D images. And project this 2D face features to the 3D point and get 3D feature points from the 2D to the 3D. And also here from this region of interest, we project them to the 3D data and get 3D region of interest. And for the second frame, we compare them with the first frame, and using these features, which we determined here, these 3D features, we make a head tracking. The head pose is determined, and if there is a strong head movement, the measurement is skipped, and we start with the next. If there is no strong movement, one can project the new located 3D region of interest onto the 2D images, and on the basis of these images, then one can extract the different biosignals. So you can see that the combination of 2D and 3D images give much more stable results and avoidance of the influence of head movement, because you can track that is shown here for a kind of summary. One have here the image, the color images for the detection of the region of interest, the 3D point cloud, combine them. If that is right, we can use the images at 780 and 940 nanometer, the thermal images, align them with the 3D data, and on the basis of the data in the special region of interest, one can calculate the biosignals. That is shown here. For example, for the PPG signal, one has the gray values, or the values, the near infrared, the gray values, and then we enhance it by the so-called video magnification and have at the end we have an amplified signal which give our primary PPG signal, and from the periodicity we can calculate here in this case the heart rate. That is it is working, I will show in the next. But the system which we have constructed or which we have built is shown here. We have here the two cameras on the left and on the right. The near-infrared cameras for the 3D scanning, the projection unit in between, the spectral camera at 780 nanometer, a spectral camera at 940 nanometer, the color camera, an illumination, LED array illumination for 780 nanometer and 940 nanometer, and the infrared camera. And that device is now used for the contactless determination of the vital signs. The results are shown here. Here you have the PPG or the intensity signal, and here the analysis of the signal, and the highest peak is the heart rate, and we have compared it also for the oxygen saturation with the ground truth. Here a finger clip based pulse oximetry, and the difference is in here for the heart rate or pulse is 1 beat per minute, and here you see the comparison for the oxygen saturation. The ground truth are the blue dotted curve, and from our system calculated are the red line, and you see a very nice or very fine correlation. And also from the change of the body temperature in the region of the nose or nostril, that is the body temperature, that is a temperature change at the nostril, and from the periodicity of this signal you can calculate the heart rate here on the right, the respiratory rate here on the right hand side. That was one example in the medical application, and then where we use multimodal 3D imaging. Another interesting application comes from industry, complete another field, and that means we use it here for object transfer in the field of assistance robotics. The problem which one have in assistance robotics is how to handle object between a robot system and a person, and this object transfer or this collaboration should be very safe. And the task which we have to solve is a person has an object, here this hammer in hand, and the robot system comes, should grab this hammer, go to another person and transfer it to another person, for example, in another room. And what one have to take into account is, especially for this kind of collaboration, that the robot system should avoid to touch the human hand by the robot. When he grabs the object, when the robot system grabs the object, he should not touch the hand. And there is a need for that of the detection of the object and also of the human body parts in 3D space in real time as an input for the path control of the robot. And especially in real time, because the person should not wait too long if the robot system can grab the object. And for that, we combine 3D data and thermal image data. It's shown here on the right hand side, and RGB color data. That is used for the segmentation of the object and the hand with this kind of multimodal 3D sensor. So in this case, our multimodal 3D sensor consists of a color camera, a thermal camera, and a 3D camera. And the idea is the segmentation of hand. For the segmentation of the hand, the temperature is used as an input data, because the hand typically has a temperature of about, or the part of a person of about 37 degrees, and the object has a room temperature, for example, 22 degrees, or maybe, for example, hot, like in this image here, where a cup of coffee should be transferred. And the aim is to find this cup of coffee in the hand of the person. And the results you see here, we are using the thermal image, where you can clearly see where is the cup of coffee. Can be very simple determined, this cup of coffee in these data. So for that, we have equipped a robotic system with a color camera, with an infrared camera, with a 3D sensor. And at the end, we have a procedure. The color camera captures the scene, and the 3D camera, the 3D data, and also the infrared camera captures the scene. And using this infrared camera, you can make a thresholding onto this picture. Using the 3D data, you can make a background segmentation, and at the end, you have only by a simple segmentation, only by a simple thresholding, you will have the human hand here, the red one, and the object. And on the basis of these data, you can make the path control, which is shown here in this data processing pipeline for griping. You have the 3D input data, the registration of these thermal RGB and 3D camera data, has this multimodal 3D point cloud, makes the segmentation of hand and object, and using this object data, you can, when you know which object that is, you can make an object modeling for the griper control, the griper post position, the griping post position determination, and using these handpoints and the combination of that, you make the movement planning of the griping process. That was an application of this multimodal imaging from the industry, and now I will come to another kind that is for the investigation of high-speed 3D measurement processes. At the beginning of my talk, I have shown this introduced this Gobo projection system for 3D measurement, and we have constructed a high-speed 3D scanning system using two high-speed cameras here on the left and on the side, and between this high-speed Gobo projection system. And with this high-speed camera, one is able to capture more than 10,000 frames per second. And the high-speed Gobo projection system is also able to project more than 10,000 images per second. And using this system, we can capture, for example, really high-speed processes, which are shown here, where a nitrogen jet impulse impact on a pillow, and you see here up to 50,000 3D point clouds per second, and you see here the change of the object, the impact. Please look here. Hopefully you have seen it. The time scale of this process, these are only a couple of milliseconds. You see the pillow and how it is changed, and here you see the time scale 20, 30, 40 milliseconds for this 3D data. But that is not a multimodal system. On the other hand, it is very well known that high-speed processes are mostly in combination or exhibit, for fast processes, exhibit temperature changes. And from static data, it is well known the combination of the so-called technique of 3D thermography. That means the combination of 3D and temperature data. And this now, which is shown here on the right-hand side, for the investigation of inflammations or quality control. And these now we have transferred to the high-speed range. That means we make high-speed 3D thermography for the investigation of fast processes. And this data, this 3D and temperature data, which we can determine, can be used then as input data for thermomechanical studies, for studies of deformation, explosions, friction processes, and so on. The equipment is shown here. We have the projection unit in between of the two high-speed cameras, which are measuring in the visible spectral range. And in between here, we have introduced a high-speed far-infrared cameras with a frame rate of 1 kilohertz. And then we start the measurement process. And as described before, the 3D data are captured, and at the same time, the thermal data are captured, which giving us a 2D thermogram, and then the 3D data are reconstructed and combined with a 2D thermogram, and at the end we map then these onto the 3D data and end up with a 3D thermogram. And now I will show you some examples. At first, a basketball player, okay, that is not of interest for technical applications, but it makes joke in the laboratory. You see here a colleague of mine, he plays basketball, he punch the ball onto the button, and what you see here, now he catch it, you see the hand, the ball hits the button, and you see here, for example, the heating of the bottom of some degree due to the impact of the ball. Also, you see here on the right-hand side the temperature change of the ball due to the hand. More technical interest is the investigation, for example, of the inflating of an airbag and how the shape and the temperature is changed, because you have to avoid a skin burning when you hit. Hopefully you will never do it when you hit the airbag. There should no burning in the face. And we have captured the 3D data of this inflating airbag. Here you see the visualization of the airbag velocity for different here in meter per second, and at the same time we capture the 3D data of the temperature data. When it starts with the inflating process, the airbag is cold, in between here 20 or 30 degrees. Then as it's open, you see the temperature change in some milliseconds, and then after 30 milliseconds, the central part become much more heated in the region of up to 50 degrees. You see here also some seams of the object, and at the end, the airbag will have a temperature in the range of 50 degrees, and so you see that there is no risk for the human due to the heat. And these data, these thermal and also these velocity data can help to optimize the airbag for different types of airbag. So now I will come to a conclusion. Hopefully I have could shown you that real-time multimodal 3D imaging, it has the use of cameras in different spectral regions and 3D sensors, the combination of these data give interesting possibilities in a couple of applications, and that is, for example, in medicine, in production, for autonomous systems, and so on, for quality control. In our opinion, this combination and the analysis of these real-time data may be interesting for a couple of applications. And I will give a short outlook to the future, that you have seen also that the most of the system in the moment are very bulky. And so one deal especially with the miniaturization of the systems, for example, using micro-optical based multi-aperture cameras. That means camera systems which capture at the same time images at different spectral regions, which are shown here. In our laboratory, we have in development camera systems which are able up to more than 50, up to in the moment up to 66 images of an object at different spectral regions. And then you have a very compact, very small multimodal system in combination with the 3D data. You have a compact multimodal 3D imaging system. Okay, thank you very much for your attention. Hopefully it was a little bit interesting for you. And many thanks to my colleagues at the Technical University in Ilmenau, especially to Mike Rosenberger, Chen Chang, Jan Chang, Paul Gerhard Dietrich, and at the Fraunhofer IOF, Peter Künstoff, Christoph Munkel, Matthias, Stefan, Christian, Ingo, Daniel, Patrick, Martin, and Henry. And also, of course, we have a couple of sponsors for these different of investigations. Many thanks to them. And thank you very much for your attention.
Thank you, Professor Notny. It's a very nice talk. So I collected several questions. So the first question is that about the temporal correlation. So how to achieve the measurement results at the accuracy of sub-pixel?
That's the correlation will takes place not only at the pixel. We make a subpixel correlation, of course, and so we can reach these accuracies. That is a normal kind of a subpixel correlation, which is very well used.
Okay. So the second question is how to realize the real-time matching between the different cameras, like between the stereo cameras, how to realize the stereo matching real time?
You mean we have these two we have this camera. You mean for the calculation of the 3D data, or what you mean?
Yes.
That is made on a graphic card by calculation, not at the normal PC. There we use a graphic card calculation, and so we can we reach this real-time capability.
So the computation are carried out on the GPU, the parallel processing, right?
Yes. Mm-hmm.
Okay. Okay. Any other questions?
I have a question, Professor Natani. Thanks for giving such an excellent talk and also coming to our conference. This is
could you speak a hi Song? Could you speak a little bit louder?
Okay. Sorry. Yeah. Can you hear me better now?
I will check my. Please.
Okay. Can you hear me better now?
Yes, a little bit.
Okay. So I have like a question. You have this multimodal system, right? Have the polarizing camera. You have this shortwave infrared camera and also thermal camera. So for that system, how much it costs to build that system?
Of course, that is in principle it is very expensive and is not useful to combine all cameras for all applications and so on. And in our laboratory, we make a check and also, of course, by some other investigation, which kind of camera you have to use. And then we will end with the lowest possible cameras for this kind of application. As we have shown for the vital sign determination, of course, in the moment, it's a really bulky system. And so for real application, we have a strong need for a miniaturization of the system and not to use single cameras. It depends on the strongly on the application at which price you will end.
Yeah, sure. Yeah. So the calibration target for the you have a calibrating target for thermal camera calibration. So you build this calibrating target by yourself, or some company fabricated that for you?
This calibration target we have made by it can be a very it's a company which make electronic equipment, and they can etch these. Very simple.
I see. Do you have the contact? Can I get the contact of them after, because I sent you email. I want to get
of course.
Yeah.
Of course.
Okay.
No problem. Of course.
Thanks. So I do. Yeah. Thank you.
Okay. Due to the limited time, let's thank Professor Gunther Notny again for the very impressive talk. Next, we will have our keynote talks at 3:05 in this meeting room. Professor Zhang Zonghua and Professor Jiang Hongzhi will chair the following session. Thank you.
Thank you very much. And
yeah, thank you.
Thank you.
Thank you.
from Southeast University. Dr. Tixing Wang received her PhD degree from Southeast University and then worked as a research fellow at Nanyang Technological University in Singapore. She is now an associate professor in Southeast University. She is a member in Jiangsu Institute of Artificial Intelligence and in Jiangsu Institute of Automation. Her research interests include optical measurement, advanced signal processing, precision engineering, deep learning, artificial intelligence, and automation. Her talk title is Some Research on Fringe Pattern Analysis. Welcome, Dr. Wang. Now it's your time.
Okay. So can you see the slide?
Yes.
Okay. Thank you, Professor Zhang, and thanks everyone for coming to my presentation. My name is Wang Chenxing. I come from the Southeast University. My lab focuses on the research on 3D imaging and 3D recognition. Some works on the intelligent transportation. But today, I will share some of my works on the fringe pattern analysis. Hope this work will help to your application or your research work. So, as everybody knows that the fringe pattern is the most important factor in the optical metrology. And because some information in the real world, such as the displacement, the surface shape, the depth, may be embedded into the face of the fringe pattern. So how to retrieve an accurate face from a fringe pattern is the most important work. In traditional techniques, the phase shifting algorithm is most popular because it is very easy and through several fringe patterns and some very simple mathematical operations, you can get a very accurate phase. But this technique is challengeable for the hardware. Maybe you have to prepare a high-speed camera or high-speed projector because you have to capture many fringe patterns at an instant. So if we can retrieve the face or some useful information from single frame, maybe it's a best choice for the dynamic measurement. That's the reason why some researchers start for the single fringe pattern analysis. So traditionally, the most classic methods for the single fringe pattern analysis is a Fourier transform. We can map the Fourier fringe pattern into the spectral space, and many components can be mapped into the corresponding spectra. But if a fringe pattern is very complex, these spectra are easily to be mixed together, so it's difficult to extract the information you want. Then some time frequency methods are performed to conduct for the fringe pattern analysis, such as the windowed Fourier transform, the wavelet transform, or the S transform, and etc. But these methods are limited by the Heisenberg uncertainty theory. That is, the time resolution and the frequency resolution cannot be achieved to the best at the same time. So in this sense, we explore another method. It is called the empirical mode decomposition. This method decomposes a signal into a series intrinsic mode functions and residue. So the steps of the EMD is performed like the first, it detects the extremer of the signal and form the upper envelope and the outer envelope. Then the mean of the two envelopes is computed and removed from signal. Then the residue will left with the smaller scales, and the residue is performed the similar steps iteratively, and then we get the more smaller scales. So these steps are performed iteratively. Finally, we can get a series IMF. So this IMF range from high frequency to low frequency. If we introduce the EMD for fringe pattern analysis, we have to resolve two issues. The first one is the most important, the grouping. That is how to classify the resulted IMF into some groups to corresponding to the fringe components of the fringe pattern. A fringe pattern can be written as expression contain background, the noise, and the phase modulated signal. So if we classify this IMF into three groups, the high frequency ones correspond to the noise, and the medium frequency ones correspond to the phase modulated ones, and the lower frequency ones correspond to the background. Then we can do the fringe pattern analysis much easily. So the issue is to determine the K1 and the K2 for the grouping. Originally, we have proposed some work to determine the K1, that is to denoise. We set some cutoff frequency to remove the high frequency noise. So this is just a simple example. The second issue problem. This problem is similar to the spectral overlapping of the Fourier transform. That is, in one IMF, there are many different scales are mixed together. So this problem will bring difficulty to the grouping because one IMF have unclear physical meaning, and we cannot decide which group this IMF belong to. So the cause of the mode mixing is the uneven distribution of the extremer. So aiming to this causing, we proposed a one-dimensional RPS EMD, the regenerated phase shifted EMD, to solve this problem. We add some sinusoids with different frequencies, and each sinusoid can make each scale distribute even. And then the mode mixing can be resolved. From the result of our method, we can see that the different scales can be separated clearly compared to the other methods. So this method is not only suitable for the fringe pattern analysis, but it also can be used for the other one-dimensional signal processing work, such as the ECG or EEG signal. So introduce the RPS EMD for fringe pattern analysis. We have to resolve another issue, the grouping. So the autocorrelation is introduced to perform the analysis for each intrinsic mode function, and from the properties of the autocorrelation, we can set criteria of to determine the K1, also the K2. So this result can be is very satisfactory, but this method is only suitable for the fringe patterns with very simple orientations. So many fringe patterns have complicated orientations. So next, we proposed a bidimensional sinusoid-assisted EMD. This is the idea of this method is very easy. We add one-dimensional signal. So now we add two-dimensional sinusoids to make the extremer distribution evenly. So the two-dimensional sinusoids is displayed like this. And the result of the BSMD, we can see that the mode mixing is resolved very satisfactory. But one problem troubled us is that the white noise, because as we all know that white noise spread over the whole spectrum. That means it's not only in the high frequency scales, in the medium frequency or the low frequency, there also will appear some noise in the spatial space. So we have to add some post-processing of the methods in the methods for fringe pattern analysis. The final result of our method, we can see that it's very satisfactory compared with other methods. For the fringe pattern captured from the real system, we can see it also can resolve the exposure and some dark intensities. The fringe can be enhanced. So the BSMD can decompose the fringe pattern into many patterns and a residue. Can we get only one pattern and a residue? Because the time will be very long to decompose many patterns. So with this thinking, we research some issues about the methods. We found that the size T is a critical factor. The extremer detection and the envelope forming, we have assisted by the morphological imaging processing method. So the structural element, the size is very important. How to determine the size T for the structural element, and how to determine the frequency of the 2D sinusoids. These are the important issues to decide the results of the BSEMD. So also, we based on the autocorrelation and perform some research. We deduction expression of the superposition of sinusoidal functions to rewritten the autocorrelation, and we can extract the T from this deduction. So these are the simulation results for the BSEMD based fringe filter. We call it is a fringe filter because it can decompose the fringe pattern into fringe and the background. So it looks like a filter to only filter the fringe. So the simulation result it seems very good in the simulation, and also for the real experiments, we can see that the second line of the result are our result. The background can be separated very clearly, and that means extracted fringe can be very accurately. So these are the BSEMD, but only if there is only one MF, the time cost is also long. Maybe it will cost 1 second for each fringe pattern. So it's not satisfactory for dynamic measurement. And we try to implement the method with the GPU by the multiple threads in CUDA. And when the size T is very large, we select the structural element with the square shape in order to separate the square matrix into the two vectors, the horizontal and the vertical. Then the speed will be speeded up very fast to speed up the convolution operation. So, but still the time is limited. We can only process fringe patterns about 50 frames per second. But so recently the deep learning methods are very popular, and we want to try whether it can solve the time problem. So we propose a deep learning method. But if we retrieve the phase from the fringe pattern, we have to do many media steps. So we want to retrieve the depth directly from the fringe pattern. So this work is transfer the fringe pattern to the depth. And the training data is a very important problem for the deep learning method, as we know that. So we introduce the graphic methods to our work. The graphic software can animation many fringe patterns combined with the 3D model database. So we can generate a large amount of training data from the graphic software and the 3D model database. This is an example of the simulation, which simulates the system in the graphic software. We can see that the camera, the projector, and the object can be set anywhere as you want, and you can adjust them freely. The below are the generative fringe patterns and the obtained maps from the 3D model. The input of the network are the fringe patterns, single fringe patterns, and the output will be the depth map. So we pick the network, we pick the generative adversary network. So one of them is pixel to pixel. This network contains a generator and a discriminator. The generator generates the result, and the discriminator identifies the result, whether the result is true or false. And during the adversary procedure, we can get the very satisfactory result. So for the generator, the unit is selected. Originally, we have got the results which are not very satisfactory, because in the results we see that the details are not very clearly. So the accurate is not very good. Then we transfer to the loss. So we add some Laplacian operator and the convolutional operators into the loss. We want to enhance the detail of the objects and the such like the edge or some details. So this is a designed loss in our network. These are the results from fringe patterns in the real system. The object and the fringe patterns are not appeared in the training data, but the predicted phase map visually it is very satisfactory. Some quantitative experiments and comparisons are still going on, so it's not presented in this presentation. So for the single fringe pattern analysis, there are many issues worth exploring. So welcome to contact us and discussing with us. Thank you for your listening.
Okay, thanks, Dr. Wang. Give us a wonderful presentation. Talk about fringe pattern analysis by using Fourier transform EMD, RPS EMD, BS EMD, and so on, also by using deep learning. Now it's question time. So anyone have any kind of question, please?
So
Okay,
Professor
first,
Wang, thanks.
you first.
Okay. So anyone does anyone else have a question?
Yes, please, Professor
Okay.
Song.
Yeah. Okay. So so Professor Wang, so for the deep learning, the recent work you did on deep learning, how many training data you need?
Training data. Because the object in our training data, we are not limited. So any object is can be included. So the data will we have 10,000 about 10,000 of the training data. Yes. Because if the data is very less, the accuracy will be decreased.
Yeah.
If you focus only one type of objects, maybe you can reduce the number.
That
yes.
How did you get that that many data sets?
How you mean how do we get the training data?
Yes.
We simulate with graphic software.
Oh,
yes.
okay, I see.
Yeah.
You should,
So we have the objects in the 3D model database. We opened in the website and we loaded it into the graphics software, and then we simulate the FFT system in the graphics software.
I see. Yeah, that makes it much more easier because you can create arbitrary situation now.
Yes. But experiments have to be analyze many issues to make the network generalized, because it's simulate. So we have to consider many issues, make the system much close to the real system.
So so you use what kind of graphic software you use? You use SolidWorks or?
You mean the software?
Yes.
We use Blender.
Oh, you use Blender. Okay.
Yes.
Okay.
Yes.
Yeah.
Because it's much easy, and it can generate the data very fastly.
Yeah. That's good idea. So they solve all the problem. Yeah. Thank you.
Yes.
Great talk. Yeah. Thank you.
Okay.
Okay. Any more question? Dr. Wang, I have one question. So according to your knowledge, what's the advantage and the disadvantage of different fringe pattern analysis method, like Fourier transform, EMD, and your proposed BS EMD and deep learning?
The difference.
The advantage and the disadvantage.
Yeah. Okay. So for the spectral-based spectral analysis-based methods, we have to assist by some manual work, such as parameter selection and the basis function for the wavelet transform or the window transform and aesthetic.
Yeah.
And the EMD is data-driven, and it's only focused on the data, determined on the data. So it is adaptive. And we perform many works on the EMD because it has problems of the mode mixing, such like things, and it is not appeared in the real application because it's very time cost for especially for the 2D world. So we perform many works to enhance the time to enhance the speed of the algorithm and resolve the mode mixing. But these traditional methods cannot be proposed very fastly. Even for our best work, we can only process about no more than 100 French patterns per second. So if the French pattern is very large, it's also very worst. So I think the deep learning method can balance the efficiency and the accuracy very beautifully. But the database is a problem of this method. So
yeah, of course, yes.
Yes. So that's the line of our work.
Okay, thank you. So,
okay.
Anyone to have any question?
I have a question.
Yes, please.
Yeah, Professor Wang's talk is very impressive. So I think the generation of the training data is a great idea. So how do you generate the training data, which is very similar to the real data?
We have performed many experiments and with considering the different periods of the fringes and the different angles between the camera and the projector. Also, we calibrate in the graphic software, much similar to the real systems. Also, you have to consider the shadow and the light and many things. So it is very large work to analyze. But the experiments, these two never appeared in the training data. The object never appeared, and also the two French patterns not appear in the training data. But the depicted results, I think it's visually satisfactory. So I think this method is can be effective in the real applications.
Yeah. I think the neural network performs well on the training data. It never saw during the training. Yeah, it's a great work.
Yes. So
thank you.
Maybe we think that the UNet is also a very powerful network. Next, we will try this network and compare these two.
Okay, thank you.
Okay.
Because of time limit, is the end of the question. Thanks, Dr. Wang again. Now we move to the next one. Next is Dr. Haixia Wang from College of Computer Science and Technology, Zhejiang University of Technology. She received her bachelor degree and PhD degree in computer engineering from Nanyang Technological University, Singapore in 2007 and 2012, respectively. She was a research fellow at Multi-Platform Game Innovation Center, Nanyang Technological University from 2013 to 2014. She is currently an associate professor in College of Computer Science and Technology, Zhejiang University of Technology, China. Her research interests include optical metrology, 3D shape measurement, image processing, and pattern recognition. The title of her talk is Acquisition and Recognition of Subcutaneous Fingerprints Based on Optical Coherence Tomography. Welcome, Dr. Wang. Now it's your time.
Thank you. Thank you, Professor Zhang. Can everyone hear me and see my screen?
Yeah.
Yes.
Okay.
Yes.
Yeah, thank you. Thank you for your introduction. And thank you for Professor Zhang and Professor Xu and Professor Feng and Professor Zhuo for inviting me to give this talk. My name is Wang Haixia. I'm from Zhejiang University of Technology. My talk will be the acquisition and recognition of subcutaneous fingerprints based on optical coherence tomography. My talk will be in 3 parts. First, I will do an introduction about brief introduction. Then I will talk about the other 2 parts. Okay, let me just start. Okay, so biometric recognition is one of the core technologies of public security. From year 2004, U.S. Embassy has required for fingerprints during the visa application, so they can do access control in entry and exit. And from year 2011, China has required for our biometric information like our face and like our fingerprint in a second generation ID card. The fingerprint within various biometric features is most widely used and now accounting for 58% of the market shares in China. So people know that fingerprints have been widely used, has been widely known, and has been widely seen as one of the most secure way to identify a person. Do you know there are still serious challenges facing by fingerprints? The first challenge is the quality of the fingerprint. Okay, so we know that fingerprints are pattern on our skin surface, pattern of the skin on our fingertip. So the skin can degrade along with the time. So the quality of our fingerprint actually, even though it is unique, its quality decreases. So at about 3 to 6% of the fingerprints are not clear according to statistics, and which this value has been proven during the second generation ID card acquisition, which means alone in China, there are 39 million of population cannot properly use their fingerprint for recognition. And if it goes to poor quality, the number increase to 10%. The conditions like jaundice, the conditions like aging, like dirt, all will cause the fingerprint recognition to fail. The other challenge we are facing now is the forgery. Okay? So when we use our finger without any mask to touch a smooth screen, we left their fingerprint. And this kind of latent fingerprint can be collected and can be made as template to make forged fingerprint easily and inexpensive. Materials, quite common materials such as latex, glue, gelatin can be used to create a forged fingerprint, and this fingerprint has successfully cracked more than like 70% of mainstream equipments. Yeah. So you can see in the let me have the cursor. Okay. So you can see in the left part of this slides, we have in our lab also made a lot of big fingerprint easily using different kind of materials for different types of fingerprint scanners. Okay. So and also even the fingerprint counterfeiting problem is considered. The anti-counterfeiting compatibility changes with the environment because the temperature, the humidity, all can change the presence of the fake fingerprint during scanning, and so increase the difficulty to identify the forgery. So researchers are seeking for ways to have fingerprint with high anti-counterfeiting compatibility. They are seeking for ways that the fingerprint cannot can be the influence of external condition can be reduced. So during this time, we found the way in our skin, as shown in the right picture, in our skin, not only surface fingerprint is presented by the corneal stretching layer, but also internal fingerprint inside the finger is presented with variable epidermis junction layer. So we can move fingerprint from surface to subcutaneous, and we can move it from 2-dimensional to 3-dimensional, so that the anti-counterfeiting capability can be increased, so that the external condition influence can be reduced. Also, besides the internal fingerprint, there is a ground called sweat ground, where our sweat come from inside to outside. Okay, so the sweat ground has an opening on the surface of our finger that is called is a third level feature of fingerprint. It is called sweat paw. Okay, so with 3-dimensional measurement of our skin, we can get more information and more reliable information for fingerprint recognition. So let's come to my second part of the talk. I will introduce about the OCT-based acquisition. So here we show the system setup of our subcutaneous fingerprint acquisition. Okay. During the system setup, we considered about 2 problems. First is that for subcutaneous 3D structure scanning using optical coherence tomography, we found out conventional OCT measures small sizes, and while for fingerprint we need to have a larger area because fingerprint has their standard size to be met. So we need to have a larger size area for subcutaneous 3D structure acquisition. And in the other hand, now the OCT-based fingerprint is still new. It's not commercialized yet. It is a new way to get a fingerprint. So the fingerprint we have from OCT need to be tested against the fingerprint we already have on the market because there are large database there. We cannot remeasure again. So we need to have a way to compare with conventional methods. So based on these 2 ideas, we designed this system. So this system compares 2 light passes. First is total reflection part. In the total reflection part, we do conventional 2D fingerprint acquisition using total reflection. In the below part, we use OCT to scan for subcutaneous volume data where we can get internal fingerprint. So this is our system, and we also have packed our system and for further testing. So for the OCT part, we get for the H scans, each H scan contains 500 pixels, and we will have 1800 of H scans to form a B scan. We have 1400 B scan images to form a OCT volume data. And with the offset property set, we measure fingertip area approximately 18 millimeter to 14 millimeter. That is required by the standard of OCT or fingerprint capturing. So in the left is the B scan images we obtained with pseudo color, and in the right is the visualization of volume data. Okay, so we can also have a closer look at the B scan image. Okay, in gray color, we can see it has different layers of structures. Okay, so from the top is the layer of the glass is a prism, layer of the prism, and inside there are layer of stretch corneal, layer of variable epidermis junction to represent the internal and the surface fingerprint. And in between there is also there are also many sweat grounds. it is a spiral-shaped thin structure representing the thread grounds. So OCT we all know OCT measures volume data. Now we know that in this volume data there are different types of fingerprints hidden there, but it cannot be directly measured. It need to be extracted. That we will talk about a little bit later. So now we show here two volume data captured, one from two finger, the other from forged finger. This volume data visualized for demonstration. So the left one is the two finger, the right one is the forged finger. From the left one, left one we see the two finger we have surface fingerprint in orange. We have internal fingerprint in yellow. In between them we have green thread grounds, many thread grounds. In the right, in the forged finger, the surface fingerprint is also clear, but inside there is nothing. So in OCT volume data, true and fake is very distinguishable. So as I just said, we have directly measured the TIR fingerprint. That is the conventional surface fingerprint. And from OCT volume data, I need to extract both the OCT surface fingerprint, the OCT internal fingerprint, and then we need to extract the subcutaneous thread grounds from the OCT volume data. And we have also performed data acquisition to establish a database for testing or recognition and so on. So until now, we have captured about 81 people, each with 6 or 8 fingers captured, and each finger is captured 6 or 8 times, so for recognition purpose. And so totally we got 1,572 sets of fingerprints, and this data set can be used for our investigation. So with this fingerprints, we have make evaluation of their qualities. Okay, so for OCT fingerprint and the TIR fingerprint, we use several criteria to measure their quality. And these are all the qualities that we commonly use to evaluate fingerprints. And we can see that they have their own advantages. And generally speaking, we notice that when our finger is under good condition, the TIR fingerprint have better quality because it measured, it do not need to be extracted. While when our skin condition is not very good, OCT fingerprint, that the internal OCT fingerprint has better quality. So that's the part of acquisition. Get the data from using OCT to get the data of subcutaneous fingerprint volume data. Then we need to perform the extraction in order to actually use them. And then we need to perform recognition. So this part will talk about the three post-processing works about this part. So the first part is actually just now we have mentioned that we need to do the extraction, and to perform the extraction actually is a work of segmentation first. So we need to do the segmentation of different tissue layers. And this work we use BCL UNet to do it. This is based on UNet as well. And in here we use we incorporate the bidirectional convolutional LSTM. So the spatial dependency between the 3D data spatial dependency between different B-scan data can be ensured, can be concatenated, and so their continuity can be kept. In the other hand, we incorporate this one called dilated convolution. That is because we need to segment the structure corneal, like here small picture in red. We need to segment the variable impedance, that one in green, and the thread grounds, where thread grounds is comparably smaller than the other two targets. So and then in UNet, we know that UNet use downsampling to get features. So in order to keep small objects or thread grounds, we need to reduce the number of downsampling, but we still need to keep the respective field large. So we use dilate convolution to increase the respective fields and without losing the information of thread grounds. And this instruction work we have just published in International Information Forensics and Security. So after the segmentation, we get the result shown in the picture here, and then we extract contours from the segmentation results, and then we use these contours to generate the fingerprints, internal and the surface one. In this slide, I show the process how we generate both some external surface fingerprint and internal fingerprint. If you have a look at here, you can see that the red one and the green one are the fluctuations of the surface fingerprint and the internal fingerprint. And if we have a line crossing them, the intensity value are changing from light to dark, from dark to light. So that will be similar as the ridge and the valley on our fingerprint. So we developed one way to get a line, to generate a line, go through the fluctuation, so to generate the fingerprint intense or intensity value. And in another look, we all know that we get depth information. Okay? So we get depth information. Depth is fluctuated. It is high and low to represent ridge and valley. So depth can also be used to represent the fingerprint. So we also has approach to get the fingerprint intense or depth. So using these two approach, we generate each for surface and internal two fingerprints, one by depth and one by intensity value. So here are some example of the surface fingerprint and internal fingerprint by intensity value. Okay, just for a demonstration that the surface and internal fingerprint, they are consistent. And there is another demonstration when we have like a damage, small damage scar, we have wrinkle at stains or water stains on the surface, then the internal one does not be affected by this kind of surface condition. Then in total, in this experiment, we established 7 data sets, 7 databases, okay, from the same 1,572 volume data, okay, each with a different setting. Okay, 4 are from the proposed, the method we proposed, the BCLU net. And the other 3 are from gradient-based method. It is a conventional method to generate fingerprints from OCT volume data. And 2 of them are generated through depth, and the 5 of them are generated through intensity values. Then we perform both on comparison to validate our method, as also we want to evaluate the recognition capability of fingerprints get from OCT data. So we perform the recognition experiment, and we use a curve called equal error rate to show the recognition capability. It is the most commonly used criteria to evaluate the recognition capability of fingerprints. So in these 2 figures are the equal error rate of the surface fingerprint and the internal fingerprint. The lower the value, the better the result. Okay, so which means the equal error is lower. So we got in here, we should tell us that internal fingerprint by intensity have lower ER than fingerprint by depth. This is probably due to the depth information need for the post-processing to be look like the ones in like intensity. We also have here in the right the internal fingerprint performance, and we compare to, we found out the internal fingerprints generally have a lower ER than the external fingerprint, because generally internal fingerprint does not be affected by external conditions. So also for the experiment, we also want to know is that one if the internal fingerprint and external fingerprint can be used together. This is our purpose in the future, that our internal fingerprint by OCT can be directly used with other external fingerprints. So we do an experiment on that, and we found out the red line represents the performance of the mixed database, and it shows that mixed data, half are internal, half are external. They can be used together, and their performance is not bad. And another thing is we want to test about the fingers. When we want to know when the fingers are under poor condition, how are the performance? And we see that when surface fingerprint is tested for the ones with poor condition, the performance is very bad. And when we use the corresponding internal fingerprint to test for the recognition, the performance increase with a very largely, like 10 times. Okay, so now our database for this database poor condition is not very large. In the future, we will perform a much larger database to get a much more reliable and meaningful data. So that's the fingerprint from OCT fingerprint. Okay, so we just now demonstrate the system. System is a synchronous acquisition system with TIR and with OCT. So we also need to have a look at the TIR and OCT fingerprint together. So here is some fingerprint from both TIR and OCT. The first line is the TIR from total reflection. The second line is from OCT, but they are both surface fingerprint. The third line is the internal fingerprint from OCT. Okay. If we see here, have a look at here, when the surface condition is good, is okay actually. The total reflection surface fingerprint is better than OCT fingerprint, OCT surface fingerprint. While it has the quality actually is also better than the OCT internal fingerprint. But when our skin condition is bad, like these two, they are all total reflection surface fingerprint. They have very severe skin wear, or their edging effect is very severe. They don't have enough information for recognition actually. But if we have a look at the internal ones, their quality is better. The details are more clear. So there's the HTLs, the OCT internal fingerprint can have great potential to amend or replace the damaged surface fingerprint. So we also perform experiment on the recognition compatibility of these three type of fingerprints. And here, the ones in blue is the total reflection fingerprint, and the one in red is our internal fingerprint. It still performs better than the external fingerprint by the reflection. So don't forget, we also have captured segmented sweat gland. So we can, from sweat gland, we can allocate the location for sweat pores, and we calculated, we get 81% true detection rate and 14% of false detection rate. This performance are still under investigation, need to be improved. In the same part, we talk about the multi-sensor fingerprint registration. Okay, so in the beginning, we talk about the synchronous acquisition. Synchronous acquisition tells that we have two light paths, or one for total reflection, one for OCT. The light paths are different, which means they have different distortions and they are under different coordinates. So we need to make them into one coordinate with one coordinate, so they can be used for matching, used for matching actually. So because of synchronous acquisition, we have because of synchronous acquisition, we can do hardware registration. So we use total reflection grid image to do the registration, and we can see that they can be generate the correction can be performed. They can be made into one coordinates, but still after hardware registration, there are still two further problems. One is the image style differences. You can see from these two images and from our previous fingerprints that the noise level, that the ridge and valley width and so on, they are different because we use different sensors, different ways to acquire them. The other one is we use here is cursor registration. We use a grid image. So this is sparse. So the cursor registration cannot finally register in very details. So one purpose of do the registration for our work is we want to study that if can external and internal fingerprint work together to generate a much better fingerprint, have advantage of both of them. So we need to have very fine registration to do that. So we have developed work to perform this task. So this work is separated into two parts. First is before registration, we do a generative adversarial network with structure constraint. We do the so-called style transfer. What is style transfer? It means we transfer the style or low contrast OCT fingerprint to the style TR fingerprint in terms of grayscale distribution, in terms of noise level, and ridge valley contrast, and ridge valley thickness, and so on, to make them look similar. They have the same style. So in this work, we do a GAM network, and we design a constraint called structure constraint. So to make sure even the style is transferred, but the detailed structure does not change. We can see from this picture, it is overlap of fingerprint before and after style transfer. Their skeleton are precisely aligned, so they are the same structure, does not change, but style changed. So after style transfer, from here, the quality or it is also enhancement of the image. So the fingerprint quality also increased. In the second step, we do the fine registration. So fine registration, we use fast digital image correlation. This is the work by Professor Jiang Zhenyu and Professor Qian Kemao, and we adopt their method and adapt to the fingerprint registration. But due to the similarity or local similarity of fingerprint, we introduce outlier rejection to make sure to exclude false matching. So we can in the last we perform this registration, fine registration very fast. And the registration accuracy is demonstrated in this two diagram. And the proposed method have retrieved the best result by comparing the fingerprint, the OCT fingerprint after registration with the TR fingerprint that it need to be registered to. So also, we also get evaluation on the matching performance, because in fingerprints, matching or recognition is the ultimate goal. So we evaluate the matching performance, and the proposed method also prove the matching scores achieve the lowest ER, the ER equal error rate. So this is some registration result. This is the TIR fingerprint. In the middle is the OCT fingerprint. In the right part is registered the OCT fingerprint. And after registration, we perform some preliminary work on fusion, which means we want to fuse the TIR fingerprint with OCT fingerprint so that the new fingerprint can get their advantages and we can have better fingerprint for future use. Okay, so this so we have this preliminary result. We can see after the fusion, the result here, the ones lost in the TIR fingerprint has been amended. The wrinkles has been mostly removed. And from this one, this is under bad condition that the skin is the fingerprint is blurred, and we can also see that with fusion with internal fingerprint, the quality has been greatly improved. Okay, in the last, let me also tell a little bit about the anti-spoofing or subcutaneous fingerprint. For
it to me, Dr. Wang. Time already. Yeah, just
okay. So it's very fast. Only one slide. Okay.
Okay.
So yeah, we also do some counterfeiting work, and we test about the ones with true finger or fake finger, and we see, yeah, it's very easy to tell if we use OCT fingerprint. Thank you. Sorry for the delay.
Okay. Thanks, Dr. Wang. Give a wonderful presentation about fingerprint recognition and acquisition. So for now, because of the time limitation, we have one question. Anyone do have any one question just?
Yeah, I can ask a quick question. So for the one, great talk, great work. So yeah, do you look at the pores of this finger, finger rings?
The finger what?
There are some pores. It's called yeah. So what resolution you capture for the image?
The resolution. We have higher than like 2000 dp dot per inch.
Or 4000?
2000 dot per inch. So the image is the image is 1800 multiplied 1400 with an area of 18 millimeter times 40 millimeter.
Okay, yeah, I was reached by someone. They really want to capture the pores, which is on the ring yeah.
Sorry, I didn't hear it clearly. These are the pores we captured. They actually we can capture quite clear. The red ones is the subcutaneous pores, the white dots, and these circle out the dots we have identified as backgrounds. So this is
the 4000 dpi or 400 dpi?
This is 2000 dpi. Yes, above 1200 like then we already can get a pause.
Okay. Yeah, they're asking me. I don't know the answer. Now I know.
Yeah. Okay.
Okay. Thank you.
Thank you.
Okay, because time limit, so now it's the end of this talk. We thank to Dr. Wang again. For now, I think we have 5 minutes short break to have coffee and tea. And at 4:15, we come back. The next session, Professor Hong Zhijiang from Beihang University will chair the section. Okay, so thanks for all of you. Now is a break.
Thank you, and sorry for the delay.
Okay, no problem. Thanks.
Okay. I'm Jiang Hongzhi from Beihang University. It's my honor to chair the next section. Firstly, let me introduce the next speaker, Dr. Weiwei Wang from Oscar University. Weiwei Wang is currently associate professor working at the School of Engineering Science, Osaka University, Japan. He received his PhD degree in robotics from the Department of Mechanical Informatics, the University of Tokyo, Japan, in 2013. His major interest is smart manufacturing, use dual-arm robots. Professor Wang serves as associate editors and reviewers in major robotics journals. His keynote title is Automatic Robotics Manipulation and Assembly by Watching Human Demonstration. Okay, let us welcome Dr. Weiwei Wang for his presentation. Thank you.
Thank you. Thank you very much for the introduction. I'm Weiwei. I'm from Osaka University. Today I'm going to talk about automatic robotic manipulation and assembly by watching human demonstrations. I guess my talk is different from previous talks since most of you are working on vision systems. But for me, I'm working on robotics. And first, I'm going to talk about the motivation, why I'm working on these projects, and I'm working on in the automatic planning using vision system in robotics. The motivation is from the challenges in system integration industrial. Conventionally, in system integration industry, we program robots using teaching pendants. Here's an example of the teaching pendants. There are lots of buttons on the teaching pendants. You press the button, move the robot to somewhere, and then move it back. And then you play the recorded motion, and then the robot is going to repeat between those key poses. Another method is using the force mode control. In this case, there are force sensors or current sensors equipped on the joint of the robots. And you can drag the robots to one pose and then pull it to another pose, and then record the poses, and the robot will going to move between those recorded poses. The third method, conventionally, the third method is virtual reality. You can program the robot in using a graphical user interface in your personal computer, and then the system will generate the motion for the robots, and you can control the robots and replay the recorded motion in the virtual reality environment. All of these methods are conventional methods. The conventional methods have a significant disadvantage. That is, first, it's not applicable to different robots. When you change the robot, we have to do everything again. We have to reprogram the robot to reteach the key poses, because the kinematic parameters and dynamic parameters are all different from robots to robots. The second point is it's not applicable to different objects. When we make products, we usually receive reservations and then prepare the products for our clients. The reservations change from seasons to seasons, and we will not be able to do the same thing all the time. We have to reconfigure the automation system for different products. And if we use the conventional method, we can only program the robot once, and it's not applicable to different objects. Many spin-outs. Since 2 or 3 years ago, many spin-outs begin to find solutions for these challenges. They use vision system together with simple motion planning to autonomously control the robot and perform pick and place tasks. Here, these two videos show the examples of the autonomously controlled robots. But there still remains problems. The problem is manufacturing is not all about pick and place. There are more general topics like assembly, packing, and printing. In my group and outside university, we are developing methods to solve the remaining challenges, especially in assembly, picking, packing, and printing. We develop a system that has 4 components. In the leftmost part is the teaching interface. The human demonstrates the motion. I'm going to move the window here to better show the words. In the left part, the human demonstrates the motion. That's the demonstration interface. And then we have the vision system. The vision component will recognize the object. And the robot system will follow the human demonstration to plan its own motion, plan its own gripping poses and joint motions. And after that, it's going to execute the planned motion. During the execution, the robots are going to perform real-time feedback, like in-hand pose estimation and force control to finally finish the assembly or printing tasks. All of the framework is based on a system we developed at our lab. The system is called WRS. It's an open source intelligent control system. It's a ROS-like system, if you are familiar with ROS. And but the difference is we use the most up-to-date infrastructure, and we make the system much easier to use. The system we build everything from scratch by ourselves. Our system has a communication component, simulation component, motion planning, grasp planning, manipulation planning, and task planning components. Also, we have the vision components and the robot drivers to communicate with a wide variety of robots. This page shows the development workflow for our system. For example, if the goal is to replace the human, the working human here, using a dual-arm robot, and then using our system, we are going to first recognize the objects using the vision component. And then with the CAD model of the object, we plan the grasps. We plan the relative poses between the gripper and the object so that the robot can pick up the object with planned grasping poses. And third, we are going to perform integrated task and motion planning using the system to generate the robot motion. Finally, we can have a system like this. First, the human demonstrates how to assemble or how to finish a task in front of the vision system. And then the robot understands how the objects moves together or get assembled. After that, using the grasp planning and motion planning, the robot can plan the grasps. For example, here the robot is trying to find a feasible grasp to pick up the object. And then it's going to plan its own motion to change the pose of the object and then assemble the object onto the final, out of the goal configuration. That's the workflow. Based on the workflow and the proposed system, we developed lots of projects. And in the remaining part of this presentation, I'm going to talk all of the previous projects we developed using this system. The first one is an example of transferring human demonstration to robots. Using here, this person is demonstrating how to pile up 3 boxes. This is the vision system, and you can see in the system, the system can understand the relative positions, the relative poses between the objects. And after that, the relative poses will be sent to a planning system. You can see in the far end, this person is demonstrating how to pile up the objects. And this is the planning interface. In the planning interface, the system is going to receive the demonstrated poses, and then it's going to plan its own motion to determine how to pick up the suction cup, and how to handover is needed or not, and change the pose of the object, and change the pose of the suction cup, and then to make sure the suction tip can be moved to the next picking pose. And then the objects will be moved to the demonstrated goals one by one sequentially. All of the picking positions and the robot motions are generated automatically. And the generated motion will be sent to the real robot for execution. I'm going to show 3 execution results here. And the robot is going to first recognize the objects using visual systems, and then it plans the grasping poses for the suction cup tool. And also at the same time, it plans the sucking poses for the tool to pick up the object. And after that, the robot will generate the motion to pick up the object, to pick up the tool, and the motion to pick up the object. And finally, the robot moves the objects to the demonstrated goals. Here is another example. The robot will automatically determine whether to use 2 arms or a single arm. For example, the first scan is relatively easy, a relatively easy task. The robot picked it up and directly moved it to the goal. For the second one, the robot has to hand over the suction cup, change its poses, and then move the next can to the goal. This is the results of the tissue boxes. I'm not going to show the details of tissue boxes. I'm going to skip it and show the next project. In this case, the human demonstrates the trajectories, not only the poses, but also the trajectory. That's why I call it the trajectory demonstration. And in the previous project, the demonstrated thing is the positions between the poses between the objects. And in this case, the demonstrated thing is the trajectory. The system will understand how the object moves when the human assembles it. And then the robot will follow the demonstrated trajectory. It will apply its own motion, and at the same time will consider the trajectories. In this way, we can implement some skillful motion. For example, in this case, the robot is going to insert and then move back. This motion is skillful. It's difficult to be directly planned. Using the demonstration trajectory, we can make use the human demonstration and then plan the complicated skills. This is the third project. In this case, I am demonstrating the robot how to use a tool. This tool is a screw fastener. It's a pneumatic screw fastener. And I demonstrated the sequence of fastening the screws. I move the tool to the first hole and then to the second hole. The robot will record the first pose, the second go pose. And then I throw the tool in front of the robot. The robot is going to recognize the initial pose of the tool. That's the red thing here. And then it's going to use the grasp planning, motion planning, and task planning to determine how to pick up the object, how to pick up the tool, and how to move the tool to the go poses, and how whether the robot needs regrasp, and how to finally finish the fastening tasks. Here shows the execution results. The robot first picks up the bolt. It uses force control to make sure the bolt is firmly picked. We use force control here because the simple vision will not be able to provide enough precision. And then, as you can see here, when the robot moves the bolt to the goal, there's still a difference, about 5 millimeter difference. The robot has to search around this area to see if the goal is if the hole is found. It's going to use, if the bolt is inserted into the hole, the robot will trigger the tool to perform the fastening action. This is the second one. When the robot moves the second bolt is is going to be installed to the vertical plate. The robot plans its motion. Probably it found some constraints. The robot cannot directly move to the second bolt. It has to do a handover to change the pose of the tool to finally be able to find a feasible motion to move the tool to the second hole. And you can see in the video, the process of searching the hole is very slow. To make it faster, we develop algorithms using deep learning. We collect data of the hole and the object. And then we learn the strategy, we learn the policies to move the pegs to the hole. And you can see here, the robot is, there are two cameras on the hand. The robot will watch the hole and then determine its motion directions and quickly move the peg to the hole. In this way, the robot is going to can save the computational resources compared to the previous project. In all of the previous videos, the robots planned its own grasping poses. This is performed by grasp planning. Grasp planning plans the grasping poses for the gripper to hold an object. The grasp planning is performed using the CAN models. And given the CAN model, the system is going to perform computation to segment the canned meshes to find the parallel, to find planar facets, and then determine the contacts. And then using the contacts, the robot is going to determine how to move the hand to the contacts and how to pick it up. We must make sure the contacts will provide enough forces for the robot to firmly hold and pick up the object. And using the planned grasps, the robot can perform handover, pick and place, and many other complicated tasks. And since the grasps are pre-planned, there are many candidates. The robot can search all of the candidates, do optimization, and generate optimal motion to perform certain jobs. The planning is for model-based objects. Also, we may have lots of objects that are modelless. We do not have models. We have, in industry, lots of objects have unknown shapes. In this case, we can use learning to determine how to pick up an object. We develop a dynamic simulator here to collect the data and to determine how to, if a certain grasp is successful or not. And then using the vision system, we get the depth sensor, depth data, and we send the depth image to the trained neural network, and then learn how to pick up some objects in the depth image. That's the grasp planning. And for the motion planning, the key point is to consider about the constraint. In all of the previous projects, we were also considering the motion planning and considering the constraints. For example, when you want to put the rings onto the branches, this object has two branches. When you want to put the rings onto branches, if the branch is facing downward, and then the rings will easily fall off the branches. There is another example is to fill up a plate using 4 boxes. And it's the same. When you put the boxes, drop the boxes on the plate, you have to make sure the boxes are facing upward, or else the boxes will slide out of the plate. The way we do that is we consider the constraints during planning. and the robot will generate a motion to make sure the plates, all the branches, always faces upward. This is the first constraint. Another constraint about the gravity is maybe sometimes when you assemble the objects, when you build a structure, the intermediate objects might not be stable. For example, the second object here is not stable. For the first one, we can just we can directly drop it down there, and then for the second one, if we release the object is going to fall off. We have to consider about the force relations here. So in this case, the planner will ask the hand to hold the object, to support it. And at the same time, the second hand will manipulate the third object. After that, both of them can release. The system, the structure is getting stable. This is the second constraint during planning. Some other constraints, for example, this is a contact constraint. This hammer is relatively heavy. When you want to flip the hammer may slide inside the hand because of the contact models. We can incorporate this contact model inside the planner, and the planner will generate a motion like this. The robot is going to first move downward. It's going to take advantage of the geometric constraints and then constrain the forces to avoid sliding. This is also a constraint during motion planning. In the previous demos, all of the robots were stationary, and in this case, the robot is movable. It has a bipedal legs, and in this case, if the planning is not well performed, the robot is going to tumble over. And we can see there are two positive demonstrations. In these two cases, this is the first case. The robot planned the motion while considering the whole body stability. And you can see the robot is stable. And it can do handover in carefully selected poses. And in this, the third demo, the constraint was not carefully considered, and then the robot fell down. We have talked about the grasp planning and the motion planning, and talk about the constraints we have to consider during the motion planning. Using these technologies, we can develop some real-world systems, practical systems. I would say practical systems. And the first, we recognize this is the goal of this system is to arrange the tubes. There are many tubes in the tube rack. And they are heterogeneous. There are different types of tubes. The goal is to separate these two tubes using automatic recognition, grasp planning, and motion planning. The system can determine how to pick up each tube, the order, the sequence to move different tubes, and how to activate the different joints of the robot, and to finally separate those tubes. And using the system, we can change the goals easily. For example, here there are two patterns. We want to separate the, We want to separate the tubes into two different patterns. In the left part, we want to separate the smaller tubes to the upper blue region, and the longer tubes to the lower red region. And in the red part, we would like to separate them differently, with the small tubes to the left and the longer tubes to the right. We can change the different patterns and then ask the robots to generate different motion to separate them. With the help of our automatic system, autonomous planning system, the robot can automatically determine and change its motion to finally finish the tasks. And this demo shows the details of the motion planning. If we do not have motion planning, and we see in the left part, the robot has to, the motion is interpolated using with straight lines. And you can see the robot has to pick up the tubes higher to make sure there's no collision along the straight line motion. But in the right part, the robot do not need to pick up the tube very high. It's going to plan the motion. The motion might be curved. And the curved motion will help the robot to avoid colliding with the tubes. And also using the planning and the force control, we can implement 3D drawing systems. Here the robot is drawing different strokes on 3D surfaces. The robot can recognize the 3D surface, generate the motion to pick up and move the pens, and finally draw the strokes on the 3D surface. During the drawing, the robot has to consider about the force control, the real-time feedback to make sure the planned motion is correctly executed. Talking about the forces, forces is very important in controlling the robots. For example, here is a conventional packing hole problem. The robot has to consider the forces feedback from the surface. And then with the forces, the robot has to adjust itself to finally finish the packing hole task. This is not implementable by a simple vision system because there are always a slight difference or slight error caused by the vision or by pickups. With the force feedback, the robot can compensate the errors and finally finish the packing hole tasks. This packing hole force control policies can be integrated with the planning systems.
Professor Wang, excuse me,
Yes.
3 minutes left. Thank you. 3 minutes left.
Thank you very much. The robot can determine how to pick up the parts and then how to move them and finally finish the assembly tasks. I'm going to quickly skip those things and show the force control part. The robots are searching around the objects to make sure the forces meet the requirements, and finally the pegs can be inserted into the holes successfully. And here, for some other tasks, the task might be complicated. We have to design hands for these tasks. We design the hands, and using the designed hands, we can also finish the similar jobs. I'm going to skip the hand design. I guess that's not very interesting to vision researchers. Oops. And here we can also plan the motion for multiple robots. This example shows 4 robotic arms are collaborating together to manipulate a cabled object. 2 of the robots manipulate the cables while the other 2 robots manipulate the objects. Let me finish up the talk. We developed lots of projects using a system called WRS. The goal of the system is to solve the challenges in current system integration industry. With this system, we can plan understand the human demonstration, and then plan the grasp, plan the motion, to finish the task after watching the human demonstration. And the system is easy to use. Here is a project developed by second-year students, and the robot is going to recognize the domino plates, and then plan the grasp and the motion to move the plates, and finally arrange the domino blocks. Okay, thank you very much for your attention. I guess I ran out all of the time. If you have questions, I'm not sure. Thank you.
Thank you, Professor Wang, for wonderful presentation. Because time is limited, only one question can be asked. Anyone has the question?
Okay, I ask a very short question. So, Professor Wang, so actually the 3D sensing has widely used in robotics manipulation. So, but the biggest challenge for the 3D sensing applicated in the robotics manipulation, what is the biggest challenge?
Well, in manipulation, I guess it's not all about the recognition. We can make the vision system to be very precise, but once you pick up the object, there are some other factors that impair the precision. For example, there may be slippage in the hand. There might be uncalibrated fixture positions, and the other component of the object might not be well posed. There are lots of other factors that impair the precision. We have to also consider multimodal sensing systems. For example, we might consider about tactile sensors. We might consider about the force sensors. We need to use all of them to make sure the robot can robustly finish the whole task. That's my question. That's my answer.
Okay, thank you, Professor Wang.
Thank you very much.
Okay, let me introduce the next speaker, Ray Chen from Tsinghua University. Ray Chen is currently postdoctoral at Tsinghua University. He received his bachelor degree from Tsinghua University in 2014 and his PhD from Tsinghua University in 2020, advised by Professor Jing Xu. He visited UCSD under the supervisor of Professor Hao Su from 2018 to 2019. His current research interests include 3D computer vision and robots. His keynote title is Learning-Based Multi-View Stereo. Thank you. Let's welcome Chen Rui.
Thanks for the introduction, and thank the organizer for holding such a great event. It's my honor to be here and present our work. And hello audience, thank you for coming. I'm Ray Chen from Tsinghua University. Today I'm going to introduce our work on learning-based multi-view stereo. This is the outline of this talk. First, I'll give a brief introduction to multi-view stereo. Then I'll compare learning-based MVS with classical MVS, show their advantages and drawbacks. Thirdly, I'll present two of our work on point-based multi-view stereo network. Finally, I'll give the conclusion and our future research direction. First is the introduction to MVS. The goal of multi-view stereo, or MVS, is to reconstruct the dense 3D shape from a set of images and camera parameters. MVS has been widely applied in various fields, such as AR and VR. For AR and VR applications, you need to first measure the 3D scenes accurately so that you can put the virtual objects at the right place. And for autonomous driving, inverse engineering, robot manipulation, and remote sensing. For remote sensing, it's to reconstruct the detailed 3D shape of the architecture or the city from a lot of images captured by drones. There are four requirements of MVS: the range, accuracy, time efficiency, and computation efficiency. For the depth, remote sensing requires hundreds of meters, while the robot manipulation and the inverse engineering are often performed in 1 or 2 meters. For accuracy, the inverse engineering requires a highest level of accuracy, like sub-millimeters, while for remote sensing and autonomous driving, a few centimeters are accurate enough. And for the time efficiency, AR and VR requires the real-time reconstruction of the target scene, like 60 FPS, while the remote sensing and the inverse engineering could be done offline, so it doesn't matter to take hours to reconstruct the shape. For computation efficiency, AR and VR are often performed on mobile devices with limited computation power, while the remote sensing and the inverse engineering can be performed on PCs with powerful CPUs and GPUs. After the introduction, now I'd like to introduce the current classical and learning-based MVS methods. The reconstruction from silhouette is one of the classical MVS methods. In this method, it needs to first identify the silhouettes of the object in each image, and back project each silhouette into the 3D scene, and intersect back projected volumes to get the final 3D shape. The advantage of this method is that it is easy to implement and fast, and can be accelerated by using octaves. However, the drawback of this method is that you need to first identify the silhouettes. The result may not be photoconsistent even though they agree with the silhouettes, and it cannot reconstruct concave shapes. Another classical MVS method is reconstruction from photoconsistency. In this method, it searches the corresponding pixel along the epipolar line using photoconsistency. Two metrics that are usually used are NCC and SSD. The advantage of this method is that it is much more accurate than the reconstruction from silhouettes, and it is able to reconstruct concave shapes. However, it requires the texture for the photoconsistency computation, and it is sensitive to the non-Lagrangian areas, which look different in different views. Well, for objects with strong texture and proper illumination, a classical MVS method can already operate very well and measure the 3D shape accurately. There are several fundamental limitations. First, they cannot handle textureless area, where it is difficult to identify the silhouette or compute the photoconsistency. And it also cannot handle reflection, transparency, and repetitive patterns as well. However, in our daily life, we can see specular and transparent objects every day. Therefore, it is significant to enable MVS to process such scenarios for further applications. Recently, deep learning has shown great size compared with classical counterparts in various fields, such as the object classification and detection, and they make many applications possible. Therefore, people started to use deep learning for MVS to address the problems I mentioned before. The first work that used deep learning for MVS is Zamta's work in 2015. They used CNN to predict the matching cost of two local image patches in two views. In this work, they just replaced the predefined photoconsistent metric with the learned function, and the post-process remains the same. Therefore, their method is not end-to-end. The first end-to-end learning-based MVS method is proposed by Kendall in ICCV 2017. In this method, they built two cost volumes and used 3D scenes to predict the disparity between two rectified images. Therefore, the network can be trained end-to-end with the supervision on the disparity map. For the unstructured multi-view stereo, where the images are captured at arbitrary viewpoints, Yao proposed to build a cost volume in the reference camera frustum and warp the source image features into the cost volume using differentiable homography, and use 3D scenes to precise the cost volume to get the depth map prediction. There are also some concurrent work with the similar network structure, like DPSNet and DeepMVS. The advantage of learning-based MVS is twofold. First, they use the learned feature instead of predefined feature, leading to more robust matching Secondly, they can combine the shape pairs in the learning process. Therefore, they can get a more complete reconstruction. One key component of all the learning-based MVS method I mentioned before is the 3D cost volume. However, since the memory consumption of the cost volume is cubic to its resolution, these kind of methods are not feasible for high resolution and accurate reconstruction. In order to overcome the problem of current cost volume-based MVS method, we introduce our point-based multi-view stereo network. Before we go on with our work, I'd like to introduce more details about cost volume-based MVS, so we can get a better understanding. Firstly, they build a 3D cost volume in the reference view frustum. Secondly, for each voxel in the cost volume, the multi-view images features are fetched and aggregated into one feature vector. Once we get the feature-augmented cost volume, we apply dense 3D CNNs to regress the target surface. One question is that, are all these 3D CNNs necessary? Actually, the target scene of the MVS is sparse in the 3D space, and most of the CNNs that are performed on voxels far away from the surface are not necessary and do not help the depth prediction. Therefore, we propose to use point cloud to present the target surface. The point cloud representation is more suitable for sparse occupancy and is more memory efficient and flexible. This is the architecture of our point MVS net. Firstly, we estimate a core steps map from viewed images. Here, we use a cost volume-based method to get a cost depth map. However, since the resolution of the depth map here is very low, the memory consumption of the cost volume is not high, and the computation is very efficient. After we get the core depth map, we refine it using our point flow module. I noted that the refinement with our point flow can be performed iteratively, so we can get a denser and more accurate point cloud step by step. Firstly, we unproject the core steps map using camera parameters to get the initial point cloud. Secondly, we fetch the image features for each point in the point cloud to generate the feature-augmented point cloud and predict the point flow, the offset of each point to the ground truth surface. First is the point feature. In this work, we use the same multi-view feature aggregation function as MVSNet. That is the image feature variance among different views as the point feature, which is invariant to the order of views and encode image appearance difference explicitly. And in order to facilitate the modeling of network, we propose point hypothesis that we generate a sequence of points with different displacement along the reference camera direction. Then we use H-con and graph neural net to process the feature-augmented point cloud, such that each point can utilize the information from its neighborhood and local geometry information to predict the probability of each point hypothesis. And the final point flow is predicted as the expected displacement. After we get the point flow, we can move the points and update the depth map. The supervision is the L2 loss between the ground truth steps and the depth map prediction of each step. Now let's see some results. We first evaluate our work on the DTU benchmark, which is a widely used MVS dataset of daily objects such as toys, foods, and building models, and it contains 49 views per scene. For the reconstruction quality, our method outperforms state-of-the-art learning-based MVS method, like MVSNet, and also the traditional methods. Thanks to the efficiency of the point cloud representation, the depth resolution of our method is almost 5 times as big as MVSNet, while our memory consumption is even smaller. As shown in this figure, our method can reconstruct more geometry details than state-of-the-art. Also, compared with the traditional method, our method can get more complete reconstruction thanks to the deep learning. And moreover, due to the flexibility of the point cloud representation, we can choose to only refine the depths in the region of interest instead of the whole depth map, which is very difficult to implement for cost volume based methods. To conclude our work here, the target surface of MVS is sparse in the 3D space. Our point MVSNet processes the target surface as a point cloud directly, saves unnecessary computation, so we can achieve a better time and memory efficiency. And by refining the depth prediction iteratively, we can get a denser and more accurate result. Then we introduce our visibility-aware point-based multi-view scenario network, which is the extension of our ICCV work. In our point MVSNet, we use the same multi-view feature aggregation as MVSNet. That is the feature variance among different views. Therefore, it doesn't consider the visibility issue that for some pixel in the target view, it may not be seen in some other views that may be occluded or out of the field of view. This is very important in the MVS task. We claim that an effective multi-view feature aggregation structure should meet the following 4 properties. First, an arbitrary number of views. Like the number of input views can be different for training and evaluation and for each scene. The module should be able to process arbitrary number of views. Secondly, unordered. Since the 3D reconstruction result should be irrelevant to the order of input views, the aggregation module should be invariant to the permutation of source view feeding order. Thirdly, differentiable. The feature aggregation module serves as an interface between the image feature extraction and the 3D geometry estimation. Therefore, it needs to be differentiable such that the whole network can be trained end-to-end. And last but not the least, the robust to the invisibility. The invisible views, including the occlusion and out of the field of view, will obstruct the photo consistency computation across views for the ground truth surface. Therefore, the feature aggregation modules need to take each input visibility into consideration. Therefore, we construct 3 visibility-aware multi-view feature aggregation modules, the width average, width max, and the width variance. For the width average, we first concatenate each source feature with the reference feature and use MLP to process the feature. Then we compute the average as the warped feature. The width max is similar to the width average, where we use the element-wise max pooling instead of the average, such that we can preserve the most significant one for further depth prediction, while excluding others, which improves the robustness to the occlusion and highlights. For the width variance structure, we first use the network to predict the visibility of each view independently. Then the warped feature is computed as the appearance variance across all visible views. And by replacing the previous module with the visibility-aware version in both the coarse depth prediction and the point flow module, we show the architecture of our VA point MVSNet. Well, since the ground truth depth in the real dataset may be incomplete. We first built a synthetic dataset using Blender and 3D shapes from the YCB dataset. As shown here, the green part are the visible region, and the red parts are invisible in the reference view. In this figure, we shows the depth prediction result of our visibility Y version versus our previous version. It can be seen that by considering the visibility, we can improve the depth prediction accuracy, especially in the invisible region. In this figure, which shows the result on the DTU benchmark. The visibility version further improves the reconstruction quality. Finally, we show the reconstruction result of our method on the tanks and temples, which is an outdoor dataset for multi-view for MVS. It is to be noted that we do not fine-tune the network on this dataset. We just use the network trained on the DTU dataset, which is the indoor and short-range dataset. So from the result, we can see that our network can generate very well. To conclude our work here, our VA point MSNet uses the per-view pixel-wise visibility mask for the multi-view feature aggregation to address the visibility issue. It leads to the improved reconstruction quality, especially in invisible regions. So here comes the conclusion. There are 4 requirements of MVS: the depth range, accuracy, time efficiency, and computation efficiency. The learning-based MVS can get a more robust matching and more complete reconstruction compared with the classical method by learning to use learn the materials in the dataset. Since the target surface of MVS is sparse in the 3D space, the point cloud is efficient and flexible representation for the multi-view stereo. And also, consider the visibility of each view will lead to a better reconstruction quality. For our future work direction, we consider that currently, one thing that hinders the development of our learning-based MVS is the requirement of the large-scale dataset with the ground truth steps, which is very costly and time-consuming to get from the real sensors. In order to overcome this problem, we consider 2 possible directions. One is to use the unsupervised learning, which do not need the ground truth steps. The other way is to use the synthetic data, which we can generate as many data as we like from the renderer. However, in this direction, we need to address the sim to real issue because the appearance difference between the synthetic data and the real data we captured in our real life. Another direction is to use the semantic information and shape parameters for the MVS. Like maybe in another work I don't present here, we try to use the normal to refine the MVS result. And maybe in the future, we would like to use the with the part information or the category information to constrain our MVS prediction to get a better result. The last is the network acceleration, including the pruning and the model quantization. Because we want to improve the time efficiency and the computation efficiency for the learning-based MVS method so that it can be more practical in the real applications. That's all for today's talk. Thank you for your attention. For more details, you can visit our project page. The code has been released. Questions are welcome.
Okay, thank you, Dr. Chen, for wonderful presentation of a point-based MVS network. Okay, anyone has a question? Okay, I ask a question. What accuracy of matching points of different images using MVS network? Thank you.
Thank you for your question. Actually, we do not measure the disparity error like in the pixel. We just measure the final shape error, like the distance between the ground truth shape and our predicted shape. We do not measure in the pixel space.
Okay.
But I think it should be like 0.3 or 0.5 pixel maybe. Yeah.
Okay. Okay. What time do you cost for do with how many pictures? What time?
In like first we use the three views for the training and 5 views for the reconstruction for the evaluation, and the time cost of our method is like, since our method is an iterative method, the time cost depends on how many iterations you take. If you take like 2 iterations, the time is maybe 1 second, and if you take three iterations for denser reconstruction, the time is like 3 seconds. 3 seconds for 5 views.
Furthermore, what's the resolution of the image?
The resolution of the image is let me show here. I think it's maybe 1000 by 1000. Nearly,
Okay.
Yeah.
Other question? Okay. Thank you, Dr. Chen.
Thank you. Thank you.
Thank you. The next is the closing ceremony. Let us welcome Professor Wang to chair. Thank you.
Hello, everybody. So our closing ceremony will start within 5 minutes. So please, so our award committee is working right now. Okay, 5 minutes. to delay a couple minutes because the invited session just closed a couple minutes ago. So our committee is okay. Professor, can you share your screen? Oh my God. Yeah.
Hi, Professor Xu. Can you see me now?
Okay. Yeah, I can see,
Yeah.
and I can also hear you. Okay.
Okay,
Everything
sorry.
is ready? Okay.
Yeah, everything is ready. Sorry for the delay.
Okay, no problem. Okay. So, good evening, good night, or good morning, depending on where you are. Ladies and gentlemen, so our closing ceremony will start shortly. So, I'm Jin Xu from Tsinghua University, one of the organizer committee members. I'm honored to host this closing ceremony. On behalf of the organization committee, thank you for coming to the first International Forum on 3D optical sensing and applications. The number of registration is more than 1,300. So the attendance come from Australia, people of China, people Republic of China, Germany, Japan, New Zealand, the United Kingdom, and the United States of America, Singapore, and other countries. The conference is broadcast for Bilibili, YouTube, Google Meeting. The peak number of audience in Bilibili is more than 5,000. I think we have a very impressive weekend. So during the past 2 days, all the participants given up the time with the family or his friend or her friend. A few attendants in the US stay up later, and a few attendants in the Europe get up early for this conference. I think it was doing that because everyone has learned a lot from this conference. I think no matter what you are interested, academic or industrial issues, you can learn a lot from this conference. Thank you for your coming. Firstly, I will introduce Professor Cao Zuo from Nanjing University of Science and Technology. Professor Cao Zuo is one of the organization committee members. He will give a conference report. Welcome, Professor Zuo.
Okay, thank you so much, Professor Xu, for the introduction, and good afternoon, everyone. I'd like to say we have reached the end of our first international forum on 3D optical sensing applications, iFOSA 2020. And here I would like to give you a short report from our program committee. In this conference, it's our great honor to have so many world-renowned scientists, researchers, and young students to provide us so many fantastic presentations. So for the plenary talks, we have 4 world-renowned scientists from George Babsitas from MIT, and Professor Richard from University of Nottingham, and the CEO of OBIC, Howard Huang, and Professor Notini from Germany. So we have 16 keynote talks. They are all rising stars and young scientists in our optical metrology community. And we also have 24 invited talks from our very outstanding students, and from their very excellent performance, we believe that we will have a very promising future of our community. So we have 24 session chairs and a lot of volunteers, and thanks so much for their extraordinary service. Next, I'd like to tell you our conference award. So because we have some student competition about their very excellent talks given by all of our very young scientists and students. So we have organized a award committee. So Professor Junfei Dai from Zhejiang University is the chair of this committee, and we have 4 committee members. Professor Fen Zexing from Beijing Institute of Technology, Professor Liu Lei from Henan Technological University, Yu Lei from Henan Technological University, Professor Jia Zhenzhong from Southern University of Science and Technology, and Professor Zhong Ming from Chengdu University of Information Technology. And the selection criteria, actually, we have 2 categories of the presentation award. They are Best Oral Presentation Award and the Most Impact Award. For the first one, so the criterion is composed of 4 different aspects. Presentation is 25%, innovation, experiments, and application. For the Most Impact Award, so it's voting by the audience by scanning the QR code. I think everybody is quite familiar. I'd like to reveal the winner for the Best Oral Presentation Award. The first winner is Zhou Jiewu from Sichuan University. The title of his presentation is High-Speed 3-Dimensional Shape Measurement Based on Robust and Efficient Gray Code Coding Strategy. Second one, Xiaowei Hu from Tsinghua University. The title of the presentation is Large Depth of Field 3D Shape Measurement Inspired by Computational Imaging. And the last one, Yufang Wang from Beihang University. The title of the presentation is the application of point spread function for fringe projection topolometry. For the Most Impact Award, and the first winner is Zheng Qini from Fudan University. The title of his presentation is Analyze and Compensation of Aberration-Induced Errors in Phase Measuring Deflectometry. Second, Zexuan Zhu from University of Auckland. The title is Augmented Reality Assist Machine Process for Smart Manufacturing. Finally, Xiaohong Liu from Hebei University of Technology. The title is Optical Measurement of Diffuse Specular Surface by Combining Fringe Projection and Phase Deflectometry Techniques. I think we should congratulations for all the award winners. Finally, I'd like to mention that because we have a very big success for our iFOSA 2020, so I think this conference series should never stop, should never close. So we will have a new conference, so far 2021, which will be here in Shenzhen, China, and coming for next year, the summer of next year. And I would like to invite Professor Yu Fu from Shenzhen University to give a brief introduction for the next year's conference. So Professor Yu Fu, can you hear me?
Yeah. Yes.
Okay, I will show you slides. Okay.
Good afternoon, everybody. My fellow colleagues and postgraduate students, my name is Fu Yu, the Deputy Director of Institute of Intelligent Optical Measurement and Detection, Shenzhen University. We already have a wonderful online conference these 2 days, and after discussions with the organizer, especially Professor Zhang Song of Purdue University, we decided next year's iFOSAs will be held by Shenzhen University. It will be organized by the Institute of Intelligent Optical Measurement and Detections, and together with Orbeck 3D Technology, famous companies in Shenzhen focusing on the 3D imaging. And as you know that the Shenzhen is major cities of Guangdong province, China, and just next to Hong Kong. So it's quite convenient. As you know, recently it just celebrated its 40th anniversaries of becoming a special economic zones, and President Xi Jinping visited the cities last week. And Shenzhen is also an international hub of research and innovations in China, and the cities is homes to several notable institutes such as Shenzhen Universities and Southern University of Science and Technology. And Shenzhen University was founded in 1983. Since its foundations 37 years ago, Shenzhen University has been committed to reforms and rapid development. And it's now it is already a comprehensive university with 11 disciplines in totals, and optical engineering is the best disciplines of Shenzhen University. Its ranking is always the highest among all disciplines. And Shenzhen University is boasted of many eminent world-class scholars. And our institute, so you can switch to next.
Yeah, okay.
Yeah. The Institute of Intelligent Optical Measurement and Detections, IOMD, was founded actually only 2 years ago by Professor Yu Qifeng and academicians of the Chinese Academy of Sciences. Since its foundations 2 years ago, IOMD has been rapidly developed. Now we have a strong research teams with 22 permanent researchers, 11 postdocs, and more than 80 postgraduate students. We also have undertaken a number of key research projects from MOST and NSFC. We have also established 2 Shenzhen key laboratories. One is the key laboratories of intelligent optical measurement and perception. Another one is a key laboratory of micro nano measuring and imaging in biomedical optics. So I'm making an advertisement here. We have different positions of postdocs, research staffs, and academic staffs open to all the talented in the world. If you are interested, you can contact me by my WeChat account, Fuyu, F-U-Y-U Optics, Fuyu Optics, or email address fuyuoptics@gmail.com. Okay. Okay, at last, on behalf of the organization committees of iFOSA 2021, I welcome all of you to Shenzhen next summer. Thank you.
Okay, thank you, Professor Fu. Yeah.
Yeah, maybe we can take a group photo together. What do you think? So to stay till the last minute.
Okay.
Would that be okay, Professor Xu?
Yeah. Okay, no problem. Everybody can.
Turn on the camera so
Yeah. Tang, 志恒堂, are you online? Is there any volunteer can take a picture for us?
That look like it's
Ready?
They are doing it.
Finished? Yeah, maybe I think finished. Okay.
Yeah.
Okay. Thank you. Thank you. So at the end of the close ceremony, so I will say thanks to everybody. Not end. Okay. You want to talk?
Not yet. They are just still trying to, at least from what I see, they're still working on it. We should put a Professor Fu Yu in the middle.
Never mind, it's okay.
Oh, I see. Okay, he's trying to make it like in the frame. Looks nicer.
Yeah. Everything is done. Everything is done.
It's done already? Okay.
Yeah. The photo has been taken. Okay.
Okay. Go ahead.
Professor Zhang, do you want to say something?
I'm not very conscious, so I would rather just say thank you, everybody, for staying till the last minute of the conference. And certainly, Professor Xu, you did the hardest work for the conference. So I know how many, I do not know how many nights you work with your students to figure out all the technical problems and solve all these unknown issues. So it's a lot of details. I couldn't imagine we will have this conference without you and your students. Thank you, Professor.
Okay, thank you. Thank you.
Also,
actually, not
yeah.
only my students. So actually, all the volunteer.
Yeah, all the volunteers.
Just like what you said. Yeah, it's very difficult to organize this kind of conference, especially in this epidemic. Okay, so this is our first time to organize an online committee, online meeting or conference. So just like this. Actually, before the day of the opening ceremony, I'm too nervous to fall asleep because I don't know what happened. Because our students, all the volunteer, not professional with on living streaming. So I don't know what technical problem will happen. So it's very, very nervous. Luckily, the conference is very, very successful.
Yeah. Yeah, and I think we Professor Xu and Professor Zhou and Professor, we set up the very good platform for next year. So everything, Professor Fu Yu, of course, you need to spend more time to make it better, right? So
never mind. Next year. That's next year. I don't know whether it is still online or offline, or we can do something. Maybe some of the students in China can come to Shenzhen.
Yeah. I hope we can do it like at least some in person, right? So this online is very strange. So,
yeah, online and offline. Yeah, face to face. I think is a good choice.
Yeah, we have all the platform now. At least we figure out. So
yes. Don't worry about it.
Yeah, it will be, we know you can do it well, so no pressure. First, do you want to say something to everybody here? And also press the phone?
Yep. Thanks, Professor Zhang, to give us the opportunity to join this very wonderful online conference because of COVID-19, so we can only meet online. And thank you, so I didn't do so many things. So I think the Tsinghua University has done a lot of works for organizing everything.
No, we do everything together. We do everything together.
Yeah.
Not just one.
Yeah. So hopefully next year, so we can also provide our support to Professor Fu to help organize this next year's Art Sophie 2021, and hope we can meet physically instead of online.
Yeah, welcome to Shenzhen.
Yeah.
Hope see you.
Yeah, we can have a lot of students to join.
So, with the phone, do you want to say something?
Hi. Yes. I would like to express my greatest gratitude to all of the speakers and Professor Xu at Tsinghua University and Professor Zhang at Purdue University. Actually, just like Professor Xu said, he can't fall asleep. Difficult for him. I have the same feeling. Actually, it is also for me the first time to participate in such a big scale international forum. So, and from the result, I think we all experience very very expressive talks, and we have learned many new knowledge from these activities. And I hope in next year we will have more and more people to participate in the conference and let people know our works. Thank you.
Anyone want to make any remarks or comments?
Professor Chen?
Professor Chen, he's asking you.